And we moved to a more technical presentation, which of course would have fit better in another part of the program, but we had to deal also with time zones. So here you have it. And well, the presenter, it's Devon McIntosh, and he has a background in physics and especially in the superconductivity field. And he has worked a lot for the research and development sector. And now he's focusing on small wind turbines. Devon, are you there?
Yes, I am here. Thank you.
Welcome.
Okay, so let me try sharing.
It's a little bit of noise from the microphone.
You're a little fuzzy. Yeah, some feedback a little bit.
Maybe I'm speaking too closely to it. I'm not sure. Is that any better now?
Or it looks like there is like something touching the microphone, maybe. Let's do better.
How is this? Still bad?
Yeah. I mean, we can't understand you, but of course, if you have a chance to fix that, that would be great.
Well, okay, I'll tell you what. I have another.
Try to move on the opposite side to where you are, because it increased now. Try to move towards your left.
Okay, how is this?
Maybe a little better, right? Yeah. So I guess that might work.
Okay. If it gets to be a real problem, I have another laptop right here. I can always log on with that. But let me try. Like I said, let me know if it's.
Yeah, I would say if you have the chance to change a laptop, then that would be great. We can wait a moment.
Okay, sorry about that.
No problem. We can actually use the chance now when we are waiting that there were some questions from for Fritz before. Were they? For Fritz Oaks?
I had a question for Fritz. Fritz, could you, I missed the explanation of why there's a technical split at 300 kilowatts. Was it, and I think it was regarding grid connection. Could you go over that briefly one more time?
No, that's more something from the past. In the beginning, we started here with, let's say, big wind turbines were in that time 80 kilowatts. And expanding and in an end grid or a weak grid, placing several 80 kilowatts, then there will be at some moment a maximum. And there comes this 300 kilowatt from. If it's more, it is more a rule of thumb. And if it's more, then you need to make everything smart. Because then you have problems with your wires, big currents which are too big to handle at some places, probably. So it's more a rule of thumb, and sometimes I can't find a source. It's something that sounds that everybody has in his mouth, and when you ask also at experts, where does it come from? Yeah.
Gotcha. Okay.
I don't have a certain publication in mind where it's investigated.
All right.
Okay.
Yeah, I see two of you now. I see two Rocky. So
okay.
Maybe
Okay. Yes, I am. Let me disconnect. Leave from this one. Okay.
Much better. Thank you.
All right, sorry about that. Okay, so now let me try to share my screen. This one here. Okay, and to the top. And
Perfect.
okay, okay. Hopefully everyone can see that, and that's fine. As we said, I'm Devon, Rocky McIntosh with Sonsight Wind. And I wanted to talk a little bit about our development of 3.5 kilowatt prototype turbine. And also why. Now, due to economies of scale, generally, as we know, the larger the turbine, the lower the LCOE. And so basically now there are no small turbines under about 12 kilowatts or so that's, you know, with cost of energy less than about 18 cents per kilowatt hour. And we've got a lot of potential customers that would be interested in this turbine, you know, in such a turbine that's, you know, with size smaller than about 12 kilowatts. I just have a graphic of you know, such a possible person here. You know, it's across from wind farm, so the wind is great. And wind farm is generating with very low LCOE. He's paying in this particular case, you know, 21 cents per kilowatt hour. And, you know, he doesn't need a large turbine, you know, maybe something in the, you know, less than 5 kilowatts. And so, you know, he would or she would need options. So, you know, one solution to decreasing the LCOE would be to have longer blades, right? But longer blades typically mean more massive and costly turbines because, you know, longer blades need lower RPMs to prevent the increased tip speed ratio, and power delivery at lower RPMs typically require more massive and costly generators. Our longer blades also require more massive and costly tower and foundations because, you know, we have the increased thrust from the blades, and you know, the larger thrust means more tower and foundation costs. And they also require more powerful and sophisticated overspeed control. So for instance, if we are using stall control, generator-induced stall control, which we are now, you know, get to that in a minute. That would also require more massive and costly generators. And so it's hard to decrease cost of energy if we have significantly higher cost associated with the longer blades that we're trying to use to decrease our cost of energy. So this is the problem that, you know, we saw and that, you know, we have been working on. So our path to developing 3.5 kilowatt turbine with relatively low cost of energy. So first we focused on the generator. Needed to develop a low RPM, low mass, low cost generator, and needed to generate the rated power at lower RPMs of the longer blades without significantly increasing turbine mass or cost. Also needed to maintain low RPMs for the lower thrust, because, you know, as I had mentioned, well, as is clear, the longer blades, typically would mean higher thrust, means, more tower costs and so on. So, we need to keep the RPMs low if we want to keep thrust low. And also needed a strong generator for the overspeed control via our generator-induced stall. So then after developing the generator, we developed a 3.5, well, it used to be 3, but 3.5 kilowatt turbine around that generator, with the idea that it's got the swept area of a 5 kilowatt turbine, but the mass and cost and thrust of a 3 kilowatt turbine. And then, we needed to develop a precise control system that both maximizes the energy output within the low RPM constraints, as well as provide robust overspeed control. And, it's easier for us anyway to first develop the grid-tied turbine. And, so we'll focus on the battery charging at a later time. So here's are a couple of pictures of, some of our prototype generators. Currently, we're actually using a 6 kilowatt, and the generator, has a segmented stator comprised of individual stator modules. The configuration, allows easier coil fixturing and, less copper and electrical steel. But, and this was a big but, the configuration here caused, under normal circumstance, high cog and torque. Cog and torque is the tendency of the rotor to align in the areas or right under the stator iron, and that would manifest itself in increase starting torque, higher wind speeds for starting the turbine. So that was a big issue that we had to tackle, and in order to lower the cog and torque. Because we've, I could go into details, but there's probably no point going into too much details with that. But we also encapsulated the stator for reliability and better thermal conductivity, and the support structure is also lighter. Because it's got this ring design. And in the end, we have a low RPM generator that's also low mass and can be manufactured at lower cost. This, just some graphs showing some prior test results with, 3 kilowatt and 5 kilowatt generators. So for instance, here we can see the rated RPM, 5 kilowatt rate generator, the rated RPM is like 15% less than you would expect from other typical 5 kilowatt generators, and the mass, that's significantly less. That's like 81% lower. So then after developing the turbine, and that was, I'm sorry, developing the generator, and that was a relatively long process. And it didn't stop when we then started developing the turbine around the generator, because there were still improvements there. But the next step was indeed developing the turbine around the generator. As I show here in this graphic, we're inspired by the ARE 110, as some people may remember that turbine. And we wanted to have aerodynamically efficient blades like the 110, tail furl. Also, that was in our minds simple, low cost over speed control. And also the structure of the turbine head, that was also simple. We figured, we would keep it simple and low cost. Also would use started using commercial grid-tied wind inverter with the onboard MPPT that it has, and then we did just use a simple interface box type controller with a relay for triggering the a relay for shorting the generator to prevent overspeed control. To prevent over voltage, I should say. And we figured then that the big improvement would be that our generator would allow using longer blades for more energy in the moderate winds to allow us to lower the cost of energy. And the idea is we would have a low cost 3 kilowatt turbine, with the, by the way, this last line area, this last line here there's a bit of a typo, but we want to have a low cost 3 kilowatt turbine, but that has the energy generation and thrust the energy generation of a 5 kilowatt turbine, but the thrust and mass like a 3 kilowatt turbine. Sorry about this last line down here. It's got a little confused. This is a picture of, one of our first prototypes. As you can see, we, designed and built the 5 meter diameter blade rotor, which offered, good low wind startup, and we paired it with the 5 kilowatt generator. Was built to be on Skystream Tower. And, we started field testing in Frederick County in Maryland, over here in the States, of course. We had issues with overspeed control. The overspeed control via furling is just very tricky and inconsistent. And although the blades performed well, they were somewhat noisy and also, kind of expensive. So, that would, cause an issue with our cost of energy. We kept improving, over time, switched to imported blades to lower the cost of energy, and they were also very quiet. We also updated the frame and tail. But we still had control / furling issues. We were, using a simple controller, no data processing. Once again, I show here a picture of Carlos Fernandez Bueno, because he's the one that provided the site for the testing there in Maryland. Couldn't have done it without that, and of course the funding via USDA. Completely critical for that early stage of development. And I just want to show some pictures of Carlos's site. Interesting individual. You know, he's a medical doctor, and he's also a SkyStream dealer, and he loves turbines. And I was very fortunate to get a chance to actually do some testing there. You can, of course, see, you know, the Sonsight turbine right here. Okay, so after those initial prototypes, we developed another prototype turbine, as you see here, and started field testing at Beach Mountain. By the way, this, you know, and I can't thank NREL with the CIP contracts enough. This was first of several CIP contracts that we got to develop the turbine. You know, I got a lot of help with installation because, well, the site was managed by Appalachian State University, and you know, with Brent Somerville and his grad students. But in any case, we mounted a turbine. As you can see, this one, we once again updated the frame and the tail, and we added a furl sensor, you know, to try to get better control. I see my time is really going here. Let me try and speed this up. In any case, we had, you know, we have this, and, you know, this is just a picture of the site there. Only the Sonsight turbine remains currently. And this is our present prototype that we're working with. It's got some updates on that. The most important is that it's no longer has a furling tail. It is stall controlled, and the overspeed control system, the controller is just more sophisticated. Also, as many know, providers of the inverters for small turbines like this, you know, there are no longer those on the market. So all the MPPT function we had to move into the controller, and we now have an adapted solar inverter that we're using for grid tie. Oops. Okay, this was just a diagram of the turbine. We don't need to get into that, but I wanted to show some results from earlier this year. You know, you can see that we are, you know, on track. We were on track to get roughly 3 kilowatts at 10 meter per second wind speed, but we're still improving the power curve. And so this is the no.
Yeah, we can see your little mouse arrow.
Right. I am trying to get this to move to the next slide. Okay, there we go. It was just frozen. So now we did a couple of things. We improved the tail fin. We made it larger. We also improved the power curve. And so we, you know, I've been hoping for more wind because this is a recent change here. And so these are results from earlier this month. You know, unfortunately, the wind speeds were such that, we didn't get past, average wind speed more than this. But in any case, you can see that we're on track for 3.8 kilowatts at 9.5 meters per second wind speeds, which was just very gratifying. Okay, so this is just a summary of the turbine, RPM at the rated RPM 168. I've got thrust force, turbine mass is not bad for, a turbine, the 3 kilowatt turbine, and, one that generates, such power at low wind speeds. Okay, so what I really did want to highlight is that we looked at a site, 6 meters per second average wind speed at 30 meters, which is standard. And for a 30-meter hub height here, of course, the wind speed would then be 6 meters per second, and we've showed the energy production and the turbine cost and so on. In any case, the cost of energy here is 13 cents. If we move to a 20-meter hub height, meaning then that the tower would be would cost less, because you can see the install cost decreased here. It actually goes down, and at 15-meter hub height, the cost of energy is also 12 cents, and that's because the turbine, has the longer blades where you get more energy, increased energy, I should say, in lower wind speed areas. So as the hub height goes down, the average wind speed, of course, goes down, decreases, but then the tower costs also decrease. So we have the install cost that also decrease. So basically, for a projected $18,000, we can have a cost of energy of 12 cents. Once again, I just have this in comparison to rooftop solar, as well in residential as well as commercial. So it fits very well. It's actually less than rooftop solar there. 12 cents compared to, for residential anyway, compared to 14.7 cents to 22 cents. And okay, so I know I'm past my time. This is it. Just wanted to say we are moving forward as much as we can with commercialization, and hope to have the turbine on the market by next year. This is just us, and we are we'll be looking for partners, for the market and distribution and installation. So sorry about the time, but that's it.
No worries. It was very interesting. Are there any questions? No, it seems everything was clear. Yeah.
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 This is Robert, and just a reminder that the advantage of being able to have a shorter tower only works if you don't have trees. So.
Right. Absolutely.
Yeah, I have a question from Ken. Go ahead. Might need to unmute.
Thank you. Thanks, Devon. Great presentation. Thanks a lot. I was just wondering, with regards to the availability of your generator, low-speed PMGs are really hard to come by. And we're actually getting ours from Lancor in Spain right now. So I'm kind of wondering, you know, do you see, are you going to see yourself going into production and make that available for other turbine developers? Or is that going to be an in-house thing?
Oh, okay. I do believe that there will be arrangements that we'll be able to work out with other turbine manufacturers to make the generator available. Yeah.
Okay, great. Yeah, it sounds very promising. So, you know, that would be great.
Thank you. We're trying to move ahead with trying to set up manufacturing, because everything so far has been very much on a prototype type level of, you know, fabrication. And so we just got a contract, another CIP contract that will be focused on actually manufacturing the generator. So, you know, we hope to see that. Yeah.
Well, that's great news. Congratulations on the CIP award, and let me know. You got a customer right here waiting for you.
Thank you. Thank you.
Good. Thank you very much for the presentation.